So we will be revising what we did in epifluorescence microscopy. We discussed that epifluorescence microscopy, if we break this term, epi means above. That means the light source comes from above the sample in epifluorescence microscope, and the objective lens here acts as both condenser and objective lens. Clear? So see the working principle here. So as you can see here that from the light source, which can be xenon or mercury lamp, the light passes through a lens and then the excitation filter and reflects off the dichromatic mirror into the objective lens. So where is the light coming from? Is coming from the source, which can be xenon or mercury arc lamp. Then it passes through the lens. Okay, it is passing. So number one, we can say it is a light source. Then it passes through the lens. After that, where it goes, passes through the dichromatic mirror. Okay, sorry. It will be passing through excitation filter. After that, it is passing through dichromatic mirror, and from dichromatic mirror, it is passing into the objective lens. And what is the role of objective lens? That we already discussed. Here from the objective lens, the light is focused onto specimen, which is number 6. Clear? And here the fluorescence in the specimen gives rise to the emitted light, which is focused onto detector. Okay, which give rise to emitted light, which is focused onto the detector by the same objective lens. So by the same objective lens, the fluorescence is focused onto the detector, and this will be used for excitation. Clear? So we revise the working principle of this epifluorescence microscopy once again, that light from the xenon or mercury arc lamp, it passes through the lens. From lens, it passes through the excitation filter. From the excitation filter, it reflects off the dichromatic mirror and then into the objective lens. From the objective lens, the light focuses at the specimen via the immersion medium, and this immersion medium is usually the immersion oil, which we discussed previously. Okay, above the specimen there is a cover slip, and any light resulting from fluorescence excitation in the specimen, it passes back through the objective lens, and since it is of longer wavelength than the excitation light, it passes through the dichromatic mirror. Clear? So here the excited light which is emitted, it is of longer wavelength. It passes through the dichromatic mirror. The emission filter allows light of the specific emission wavelength of the fluorochrome of interest to pass through the CCD array. Okay, only the specific emission wavelength of the fluorochrome, which is the light emitted, is allowed to pass through the CCD array where the image is formed. This is the CCD array. Clear? We will be discussing in detail once again. So last day we were talking about that the light source is a high pressure mercury or a xenon vapor lamp, and more recently lasers and LED sources of light have been used, and these emit UV into red wavelengths. Okay, and a specific wavelength of light is used to excite a fluorescent molecule or fluorophore. Okay, so to excite a fluorophore, that is which is present in our sample, a specific wavelength is required. Clear? So light of longer wavelength from the excitation of the fluorophore is then imaged. Okay, this is achieved in fluorescence microscope using the combination of filters which we talked about in that picture, and this are specific for excitation and emission. Okay, specific filters are there for excitation and emission. And there are usually three main filters. What they are? Number one is excitation filter and a dichromatic mirror. Okay, and number three is barrier filter. So three filters here we are talking about. What are they? Number one is excitation filter. Number two is dichromatic mirror, which is often said to be as dichroic mirror, and the third is barrier filter. And these are mounted in single housing above the objective lens. Okay, for example, the commonly used fluorophore, which is the example, is fluorescent. It is optimally excited at a wavelength of 488 nanometer and it emits at 518 nanometer. So what we can conclude from here, that the emitted light is having the higher wavelength. Understood? Emitted light is having the higher wavelength. Now this is very interesting to note that the filters which are present, say for example the exciter filter. This exciter filter is made in such a way that it allows only maximum amount of 488 nanometer light to pass through it. Okay, it allows only 488 nanometer of light pass through it. When we are talking about fluorescence, then we have to note down that the excitation filter used here is allowing only 488 nanometer of light to pass through it. Okay, so the 488 nanometer light, it is then directed to the specimen via the dichromatic mirror, the same principle which we discussed. So any fluorescent label which is there in our specimen, it is excited by 488 nanometer light. Okay, so that means if you studied, if you just have seen the picture above, from the light source through several filters, it is going through the via the objective lens onto the specimen. So if the specimen is having the fluorescence, then what happens? Then the filters allowed only 488 nanometer of light to pass through the specimen. Clear? Now since the specimen is having fluorescence, it is emitting the light of wavelength of what? It is emitting the light of wavelength of 518 nanometer. Okay, so once the fluorescence is excited, it will emit the light, and this is emitting the light in the wavelength of 518 nanometer, which returns from the specimen, passes through the dichromatic mirror which is present here, passes through the dichromatic mirror and the barrier filter which is present here to the detector, okay, which is here CCR. Clear? So this is so interesting to note down. So here the emission filters, so excitation filter is allowing only 488 nanometer to pass through it, and emission filter is allowing only 518 nanometer to pass through it, to ensure that the signal emitted from the fluorochrome of interest reaches it. Isn't it interesting, guys? If it is interesting, then please like the video and subscribe the channel, because that would encourage us to make more videos like that and to help you all beyond what is required, right? Sometimes it was found that there was multiple labeling is done. See, for example, that the specimen is labeled with 2 or more fluorochromes. Why is there use of multiple labeling? Because the fluorescence which is emitted from the specimen is too low to be detected by the human eye. Human eye cannot detect all the wavelengths, okay? It may be out of the wavelength range of the detection of human eye. Human eye may not be able to detect specific wavelength which is emitted by the fluorochrome. So for example, in case of far red wavelength which the human eye is not able to detect. Okay, that is why multiple labeling is done most of the time. Okay, so a sensitive digital camera is used as a detector because human eye is not able to detect many wavelength of lights. So sensitive digital camera, when it is allowed to be used as a detector, it can easily detect such signals, for example CCD or a PMD. Understood? So this was all about the epifluorescence microscopy. If you have understood, then please click the thumbs up sign.